Look up at the night sky. What do you really see? A vast, unchanging canvas of stars. Think again. The universe isn't static. It's alive, stretching like warm taffy, pulling galaxies apart in a silent, unstoppable dance. Right now, as you sit there, the fabric of space itself is expanding, carrying entire clusters of stars away from each other faster than the speed of light. Sounds impossible, right? Yet, this isn't science fiction. It's one of the most profound truths of our cosmos. The universe isn't just growing, it's accelerating, defying gravity's pull, and rewriting the rules of physics as we know them. And here's the wildest part. This expansion isn't just happening out there. It's woven into the very atoms of your body, the air you breathe, even the screen you're staring at. How did we discover something so mind-bending? Picture this: a century ago, astronomers thought the Milky Way was the entire universe. Then Edwin Hubble peered through his telescope and spotted something astonishing. Galaxies weren't just drifting. They were racing away from us, their light stretched into redder hues like cosmic breadcrumbs trailing behind them. That redshift became the first clue that space itself was stretching, a revelation so radical it turned science upside down. Today, we know this expansion isn't just real, it's speeding up, propelled by a mysterious force we call dark energy, an enigma that makes up nearly 70% of the universe's energy budget. And yet, despite decades of research, we've barely scratched the surface. That's where this journey begins. Over the next few minutes, we're diving deep into 30 astonishing facts about the expansion rate of the universe, facts that will warp your sense of scale, time, and reality itself. From the moment a single equation predicted the universe's growth before we even had proof, to the chilling future where galaxies vanish beyond an invisible horizon, leaving Earth stranded in an empty void. This isn't just about distant stars, it's about us, how every second of this expansion shapes the fate of galaxies, planets, and even the chemistry of life. So buckle up. By the end of this, you'll never look at the night sky the same way again. Imagine living in a world where the universe was considered small, static, and unchanging, until one man's observations shattered that illusion forever. In 1929, Edwin Hubble made a discovery so monumental it rewrote the textbooks. Peering through the 100-inch Hooker telescope at Mount Wilson Observatory, he noticed something peculiar about distant galaxies. Their light wasn't just dimmer, it was shifted. Like a siren's pitch dropping as an ambulance speeds away, these galaxies appeared redder the farther they were from us. That redshift meant they weren't just drifting in space, they were racing away, carried by the fabric of the cosmos itself. This wasn't just about galaxies moving. Hubble realized space itself was stretching like dots on an inflating balloon. The farther apart two galaxies were, the faster they seemed to recede, a relationship so precise it could be described by a single number, the Hubble Constant. Think of it as the universe's speedometer, telling us how fast cosmic distances grow over time. For the first time in history, humanity had proof the universe wasn't eternal or fixed. It had a beginning, and it was evolving. The implications were staggering. If galaxies were fleeing, tracing their paths backward would lead to a moment when everything was compressed into an unimaginably dense point, what we now call the Big Bang. Hubble's work didn't just change astronomy, it demolished centuries of assumptions. Even Albert Einstein, who'd once tweaked his equations to keep the universe static, called his own reluctance the greatest blunder of my life. Yet Hubble's constant was just the first clue in a mystery that's still unfolding. Today, we know that number isn't just a fixed speed, it's a puzzle. Different measurements give slightly different values, hinting that our understanding of cosmic expansion might be missing something profound. Could unseen forces be at work? Or is our entire framework of physics incomplete? One thing's certain, Hubble's revelation was the spark that lit the fuse of modern cosmology. Without it, we'd still be staring at the stars, unaware they're racing into the darkness, carrying the secrets of the universe with them. Here's how the universe leaves its fingerprints on light itself. When a galaxy races away from us, its light doesn't just fade, it stretches like a cosmic slinky being pulled apart. This phenomenon, called redshift, transforms the light's wavelength, shifting it toward the red end of the spectrum. It's not because the galaxies are red. It's because space itself is expanding between us and them, warping the light as it travels. Think of it like drawing dots on a rubber band. If you stretch the band, the dots move apart, but not because they're crawling. The fabric between them is expanding. Now imagine each dot is a galaxy and the rubber band is space-time. The farther apart two dots are, the faster they seem to recede as you stretch the band. That's exactly what's happening across the cosmos. The light from those distant galaxies gets stretched mid-journey, arriving at our telescopes stretched and redder than when it left. But redshift isn't just a visual quirk, it's a speedometer for the universe. By measuring how much a galaxy's light has redshifted, astronomers can calculate how fast it's retreating. The wildest part, the farther away a galaxy is, the faster it appears to move. This isn't because galaxies are accelerating through space, but because more expanding space lies between us and them, amplifying the effect over vast distances. And here's where it gets eerie. Some galaxies are so far away, their light is stretched beyond the visible spectrum entirely, vanishing into infrared or even radio waves. It's as if the universe is erasing them from our view, not by dimming their light, but by stretching it into oblivion. This redshift is our most direct evidence that space isn't just big, it's actively growing, carrying galaxies along for the ride whether they like it or not. Yet redshift holds even deeper secrets. It doesn't just tell us the universe is expanding, it reveals when that expansion began. By backtracking the motion of galaxies, we can trace their paths back to a single point, the moment everything burst into existence. Without redshift, we'd have no way to measure the age of the cosmos or predict its fate. It's the universe's way of whispering its history to us, one stretched photon at a time. Scientists once believed the universe's expansion was like a car coasting after hitting the brakes, slowing down over time as gravity pulled everything back together. Then, in 1998, two teams of astronomers made a discovery so shocking it flipped cosmology on its head. While studying distant supernovae, they expected to find the universe's expansion gradually decelerating. Instead, they saw the opposite. The cosmos wasn't slowing. It was accelerating, as if some invisible foot had slammed on the gas pedal. This revelation was so groundbreaking it earned them the Nobel Prize and introduced the world to dark energy, the mysterious force driving this runaway expansion. Picture a firework exploding in slow motion. Normally, you'd expect the debris to spread outward but slow down as gravity tugs at the fragments. Now imagine those pieces suddenly speeding up, defying gravity's pull as they rocket away faster and faster. That's essentially what's happening across the universe. Supernova stellar explosions so bright they outshine entire galaxies serve as cosmic mile markers. By measuring their brightness and redshift, astronomers can gauge how fast the universe was expanding at different points in history. The data revealed a pattern no one anticipated. Supernova farther away, and thus farther back in time, were dimmer than expected. Their light had traveled through more expanding space, meaning the universe's growth had been slower in the past. The expansion rate was increasing. This wasn't just unexpected, it was revolutionary. Gravity should have been putting the brakes on cosmic expansion, pulling galaxies closer together over time. Instead, something was overpowering gravity, pushing galaxies apart at ever-increasing speeds. That something became known as dark energy, a term that hides how little we actually know about it. Dark energy isn't some shadowy substance, it's more like a property of space itself, a repulsive force embedded in the fabric of the universe. Here's where it gets stranger. Einstein's equations had actually predicted such a force decades earlier, his infamous cosmological constant, which he later dismissed as a mistake. Yet dark energy behaves eerily like that discarded idea, suggesting Einstein might have been right for the wrong reasons. Today, dark energy accounts for roughly 68% of the universe's total energy, dwarfing both visible matter and dark matter. It's the dominant player in cosmic expansion, but we still don't know why it exists or how it works. The implications are staggering. If dark energy keeps accelerating the universe's expansion, distant galaxies will eventually vanish from view, their light stretched beyond detectability. Over trillions of years, the observable universe could shrink to just our local cluster of galaxies, isolating any future civilizations in an island of stars amid an unfathomable void. This runaway expansion might even tear apart atoms themselves in a hypothetical Big Rip. Yet for all its mystery, dark energy offers a humbling lesson. The universe is far weirder than we ever imagined. What began as a quest to measure cosmic slowdown unveiled a force that's shaping the fate of everything, and we're only beginning to understand it. The universe didn't start with a gentle stretch, it exploded outward faster than the speed of thought. In the first trillionth of a second after the Big Bang, space didn't just expand, it inflated, doubling in size over and over again, like a runaway balloon pumped with cosmic helium. This mind-bending moment, called cosmic inflation, wasn't just fast, it was exponential, stretching the universe from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. And this wasn't some speculative idea. Inflation solved one of cosmology's biggest puzzles, the horizon problem. Here's the mystery. Look in opposite directions of the night sky, and you'll see regions of space so far apart that light hasn't had time to travel between them since the Big Bang. Yet these regions have nearly identical temperatures and structures. How, without inflation, they'd have no way to communicate and synchronize? It's like walking into two bakeries on opposite sides of the planet and finding identical loaves of bread, down to the number of sesame seeds, without either bakery ever knowing the other existed. Inflation fixes this by proposing that these regions were once neighbors, crammed together before the universe's explosive growth flung them apart. But inflation did more than just smooth things out. It also planted the seeds for everything we see today. Quantum fluctuations, tiny ripples in the fabric of space, got stretched to cosmic scales during inflation, becoming the blueprints for galaxies and galaxy clusters. Without those microscopic wrinkles, gravity would have had nothing to work with, and the universe might have remained a featureless sea of particles, the wildest part. Inflation left behind fingerprints we can still detect. Just as a thunderstorm leaves puddles, inflation should have generated primordial gravitational waves, ripples in spacetime itself. These waves would have imprinted a unique swirl pattern on the cosmic microwave background, the afterglow of the Big Bang. For decades, scientists hunted for this signal, and while definitive proof remains elusive, the theory's explanatory power keeps it at the heart of cosmology. Yet inflation raises its own questions. What triggered it? What stopped it? Some theories suggest it wasn't a one-time event but part of a larger cycle, with universes bubbling up endlessly in a multiverse. Others propose that inflation's energy field, called the inflaton, might connect to dark energy, linking the universe's birth to its accelerating fate. Whatever the answers, one thing's clear. The first moments of the cosmos were far stranger than anyone imagined, and their echoes shape everything we see. Dark energy isn't just a component of the universe, it's the dominant force steering cosmic expansion like an unseen hand. Picture a vast ocean where ordinary matter, the stars, planets, and galaxies we see, makes up just 5% of the water. Dark matter, the invisible scaffolding holding galaxies together, accounts for another 27%. The rest, dark energy. A staggering 68% of the universe's total energy budget belongs to this enigmatic force, a pressure woven into the vacuum of space itself, pushing galaxies apart faster and faster. What makes dark energy so bizarre is how it flips gravity's script. Instead of pulling matter together, it behaves like anti-gravity, creating more space between galaxies with every passing moment. Think of it like a rubber sheet that doesn't just stretch but generates extra fabric as it expands. The more space dark energy creates, the more it seems to multiply, a self-reinforcing cycle that ensures expansion never slows. This isn't just theoretical observations of supernova, galaxy clusters, and even the afterglow of the Big Bang all point to the same conclusion. Dark energy is winning the cosmic tug-of-war. Yet its nature remains one of physics' greatest puzzles. One leading explanation ties dark energy to Einstein's cosmological constant, a term he added to his equations to keep the universe static, later calling it his greatest blunder. Ironically, modern measurements suggest this constant might be real after all, representing the energy of empty space itself. Quantum physics tells us a vacuum isn't truly empty. It seethes with particles flickering in and out of existence. These fleeting fluctuations could generate a repulsive force, but here's the catch. When physicists calculate how much energy this quantum foam should produce, the result is a number 10 to the power of 120 times too large. That's a 1 followed by 120 zeros enough to rip atoms apart instantly. Clearly, something's missing. Alternative theories speculate dark energy might not be constant at all. It could evolve over time, growing stronger or weaker, or even interact with dark matter in ways we haven't discovered. Some models propose entirely new fields or dimensions, while others suggest our understanding of gravity itself might need rewriting. The mystery is so profound that Nobel laureate Steven Weinberg called it the most serious theoretical problem in physics. The stakes couldn't be higher. If dark energy's influence grows unchecked, it could trigger a big rip, tearing apart galaxies, stars, and eventually spacetime itself. Conversely, if it weakens, gravity might regain control, collapsing the universe in a cosmic crunch. Right now, we're stuck in the middle, watching the universe accelerate into darkness with no clear answer why. Yet every observation, from galaxy surveys to deep space telescopes, brings us closer to unraveling this invisible architect of our fate. At the heart of modern cosmology lies a discrepancy so puzzling it's been dubbed the Hubble tension, a cosmic tug-of-war between two seemingly irreconcilable truths. On one side, we have the universe's expansion rate measured by peering at nearby stars called Cepheid variables. On the other, calculations based on the afterglow of the Big Bang, the cosmic microwave background. Both methods are meticulous, both rely on Nobel Prize-winning science, yet they stubbornly refuse to agree. The numbers differ by roughly 7%, a gap that might sound small but could upend our understanding of the cosmos. Here's how the conflict unfolds. Cepheid stars are the universe's lighthouses, pulsating giants whose brightness fluctuations reveal their true luminosity. By comparing this intrinsic brightness to how dim they appear from Earth, astronomers can calculate their distance, add redshift measurements, and voila, you've got the Hubble constant, the universe's expansion rate. Using this method, teams like the one led by Adam Rees, who won a Nobel for discovering dark energy, land on a value around 73 kilometers per second per megaparsec. That means for every million parsecs of distance, space expands 73 kilometers faster every second. But then we turn to the cosmic microwave background, the oldest light in existence, a snapshot of the infant universe. By analyzing its subtle temperature fluctuations with missions like Planck, scientists can extrapolate the expansion rate using the physics of the early cosmos. This approach yields a slower value, around 67 kilometers per second per megaparsec. The difference seems minor, but in a universe governed by precise equations, it's like two clocks ticking at irreconcilable speeds. Why does this matter? Imagine building a bridge where the blueprints disagree on the length of the foundation by 7%. You'd suspect a fundamental error. Similarly, the Hubble tension hints that our cosmic blueprint might be missing a page, or that we've misread the text entirely. Some theories propose new physics. Perhaps dark energy isn't constant but evolves over time, or maybe an unknown particle type subtly altered the early universe's behavior. Others wonder if measurement errors lurk in the dust of distant galaxies or the interpretation of microwaves from space. The tension isn't just academic, it's a thrilling reminder that science thrives on contradiction. Every discrepancy is a doorway to discovery, and this one might lead us to rewrite the rules of cosmology itself. Until then, astronomers keep refining their tools, chasing the truth in the flicker of ancient stars and the whisper of microwaves from the dawn of time. The universe's ultimate fate hinges on a cosmic tug-of-war between dark energy's relentless push and gravity's stubborn pull. Depending on which force wins, our cosmos could meet three dramatically different endings, each more mind-bending than the last. First, picture the Big Freeze, a slow, silent demise where expansion never stops. Galaxies drift farther apart until neighboring clusters vanish beyond an invisible horizon. Stars burn out, black holes evaporate, and space becomes a vast, lightless graveyard where temperatures plunge near absolute zero. Time stretches into meaninglessness as the last flickers of heat dissipate into the void. This isn't some distant sci-fi nightmare. It's the most likely scenario if dark energy's current acceleration holds steady. But what if gravity fights back? Enter the Big Crunch, a fiery counterpoint to eternal ice. Imagine the universe's expansion slowing, halting, then reversing like a cosmic rubber band snapping back. Galaxies rush toward each other, colliding in bursts of blue shifted starlight. Space grows hotter and denser, cramming all matter into a shrinking volume until atoms themselves dissolve. The cosmos ends as it began, in a singularity, a superheated dot of infinite density. This scenario once seemed plausible, but since discovering dark energy's dominance, physicists consider it unlikely unless some unknown force overpowers acceleration. Then there's the most violent finale, the Big Rip. Here, dark energy doesn't just win, it goes berserk, growing stronger over time until it shreds spacetime itself. First, galaxy clusters get torn apart, then individual galaxies, stars are ripped from their orbits, planets torn from their suns, and eventually, even atoms are split asunder as the repulsive force overcomes nuclear bonds. The universe doesn't just fade, it explodes into a soup of disconnected particles, each hurled into solitary confinement across an ever-expanding nothingness. The chilling truth: we don't know which path awaits us. Current evidence points toward the Big Freeze, but dark energy remains too mysterious to rule out surprises. Its strength could fluctuate, or new physics could rewrite the rules entirely. What's certain is that the expansion rate isn't just a number, it's the countdown clock for everything that exists. Right now, galaxies are vanishing from our view not because they're dying, but because space itself is stretching faster than their light can chase us. Imagine shouting to a friend on a swiftly receding train. At first, they hear you clearly, but as the train accelerates, your voice stretches into silence. That's happening across the cosmos. The universe's expansion creates a cosmic event horizon, a point of no return where distant galaxies slip away forever, their light stretched into nothingness before it can ever reach us. Here's the crushing reality: we're already cut off from 97% of the observable universe's galaxies. Their light set off toward us billions of years ago, but because space keeps expanding during its journey, that light will never arrive. It's like running on a treadmill that's speeding up. No matter how fast you go, the finish line keeps moving farther away. These galaxies aren't just far, they're inaccessible, receding faster than light can bridge the gap. This horizon isn't fixed. Over time, more galaxies will cross it, disappearing like ships sinking below the curvature of the Earth. In 1 trillion years, any civilization born in our local galaxy cluster will peer into the sky and see only darkness beyond Andromeda. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted into undetectable radio waves. The universe's expansion will have erased all evidence of its own history, leaving future astronomers with no clue that other galaxies ever existed. Yet the cruelest twist isn't the loss of those galaxies, it's the illusion they leave behind. The light from some of these vanishing galaxies is already en route, traveling for billions of years. When it finally reaches us, those galaxies will have long since crossed the event horizon. We'll see them frozen in time, unaware they're already gone, like a letter from a loved one who passed away before the mail arrived. This horizon isn't just a barrier, it's a countdown. Every second, millions of stars cross this threshold, their light now a one-way trip to nowhere. And one day, even the closest galaxies will join them, leaving the Milky Way alone in an unfathomable void. The universe's expansion doesn't just shape space, it rewrites the future, erasing the cosmos piece by piece before we ever get to see it. Here's the mind-bending truth about cosmic expansion. Galaxies aren't racing through space like cars on a highway. Space itself is stretching beneath them, carrying galaxies apart like raisins in rising dough. This subtle distinction, called metric expansion, reshapes how we understand the universe's growth. Picture a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough itself is swelling. Now replace the dough with space-time and the raisins with galaxies. That's the essence of metric expansion. The fabric of the cosmos is stretching, creating more space between objects without them actually moving through that space. This explains why distant galaxies appear to recede faster than the speed of light, a seeming violation of Einstein's cosmic speed limit. They're not breaking any rules because they aren't moving through space. The space between us and them is multiplying. Imagine two ants on a rubber band. If you stretch the band slowly, the ants can crawl toward each other. But if you stretch it fast enough, the band grows faster than the ants can walk, even though their tiny legs haven't slowed down. That's what's happening across the universe. The ants' galaxies stay relatively still locally, but the rubber band, space, stretches so dramatically over vast distances that separation speeds become superluminal. This also means gravity-bound systems like our Milky Way or the local group of galaxies aren't being pulled apart. Within these regions, gravity overpowers the expansion, holding objects together like raisins glued in a cluster. But beyond a certain scale, dark energy's push dominates and the stretching of space takes over. That's why we'll never lose Andromeda. It's gravitationally bound to us, but eventually, galaxies outside our local cluster will vanish beyond the horizon, not because they've moved, but because the space between us has become an impassable chasm. Metric expansion flips our intuition about motion on its head. It's not the galaxies fleeing, it's the stage beneath them growing, silently and relentlessly, rewriting the map of the cosmos one stretched light year at a time. The universe doesn't play favorites, at least not on the grandest scales. This is the heart of the cosmological principle, the idea that no matter where you stand in the cosmos, the universe looks roughly the same in all directions. It's isotropic, meaning no special direction, and homogeneous, meaning no special place. Think of it like a raisin cake baked to perfection. Slice it anywhere, and the distribution of raisins appears uniform, even if individual clusters exist. This principle isn't just philosophical, it's the foundation for how we understand cosmic expansion. Without it, the Hubble constant wouldn't make sense, and galaxies might flee chaotically instead of following a predictable, redshift-based retreat. The evidence for this uniformity is etched across the sky. Galaxy surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing a cosmic web of filaments and voids stretching billions of light years. Zoom out far enough, and those intricate structures blur into a smooth, frothy sea, a testament to homogeneity. Even the cosmic microwave background, the universe's baby picture, shows temperature fluctuations of just 1 part in 100,000, a nearly perfect uniformity frozen in time when the cosmos was a mere 380,000 years old. But here's the catch: the cosmological principle only holds true at scales larger than about 1 billion light-years. Below that, the universe is gloriously lumpy. We live in the Milky Way, which is part of the local group, which sits on the fringe of the Laniakea supercluster, a sprawling structure 100,000 galaxies wide. These clusters and voids create a cosmic mosaic, but they're like individual brushstrokes in a pointillist painting. Step back and the bigger picture emerges, a universe where matter is evenly sprinkled like flour sifted through a cosmic sieve. This principle also solves a profound puzzle about our place in the cosmos. Centuries ago, thinkers like Copernicus dethroned Earth from the center of the universe. The cosmological principle takes this further, declaring there is no center, or rather, every point is equally central. An alien astronomer in a galaxy 10 billion light-years away would see the same large-scale uniformity we do, with galaxies fleeing in all directions, their light stretched by expansion. It's a democratizing idea. No location is privileged, no viewpoint unique. Yet the principle isn't beyond question. Some astronomers spot anomalies, hints of a cosmic axis, or unusually large voids that might challenge perfect isotropy. Others wonder if dark energy's quirks could hint at larger patterns we've yet to decode. But for now, the cosmological principle stands as our best compass, guiding us through an expanding universe that, in its grand design, treats every observer as equally insignificant and equally enlightened. The universe didn't always expand at the same rate. It's changed speeds like a cosmic driver alternating between the brake and accelerator. In its first moments during the inflationary epoch, space ballooned exponentially, doubling in size countless times within a fraction of a second. But then gravity took the wheel. For the next several billion years, the mutual attraction of all matter in the cosmos, galaxies, gas, and the mysterious dark matter, acted like a brake, gradually slowing the expansion. Picture a ball thrown upward. It starts fast but loses speed as Earth's gravity pulls it back. Yet around 5 billion years ago, something unexpected happened. The slowdown reversed. Dark energy, that enigmatic force woven into space itself, began overpowering gravity's grip. Like a car suddenly hitting the gas pedal on an uphill slope, the universe started accelerating again, and it's been speeding up ever since. We now live in an era where dark energy dominates, contributing roughly 70% of the universe's total energy density. Gravity, once the universe's governing force, now plays second fiddle on cosmic scales. The evidence for this speed shift is etched across the cosmos. By studying supernovae in distant galaxies, astronomers can measure how fast the universe was expanding at different epochs. The data reveals a clear curve: rapid early expansion followed by gradual deceleration, then a transition to acceleration as dark energy took control. It's as if we're watching a time-lapse of the universe's growth, with each frame revealing a new phase in its breathless evolution. This three-act structure, inflation, deceleration, acceleration, raises profound questions about the universe's fate. Will acceleration continue indefinitely, leading to a cold, dark big freeze? Or could dark energy's strength change again, triggering a cosmic U-turn? The answers lie hidden in the subtle details of that expansion curve, waiting to be decoded by the next generation of telescopes and space probes. One thing's certain: the universe's expansion rate isn't just a number, it's the story of everything written in the stretching fabric of spacetime itself. Buried in the patterns of galaxies lies an echo from the universe's infancy, a cosmic fingerprint frozen in time. These are Barrian acoustic oscillations, subtle ripples in the distribution of matter that trace back to sound waves pulsing through the hot, dense plasma of the early cosmos. Picture the universe's first 380,000 years as a seething ocean, where photons and matter were locked in a violent tug of war. Gravity would pull particles together, while radiation pressure pushed them apart, creating rhythmic waves like sonic booms that traveled outward at half the speed of light. When the universe cooled enough for atoms to form, these waves suddenly froze, imprinting their signature into the newborn matter like a phonograph record pressed into cosmic history. What makes these oscillations so valuable is their predictability. The physics of those early sound waves left behind a universal scale, a standard ruler, about 500 million light-years long. By surveying millions of galaxies, projects like the Sloan Digital Sky Survey have spotted this ruler etched into the cosmos. Galaxies today are slightly more likely to be separated by this exact distance, a statistical preference that reveals how much the universe has stretched since those primordial waves were trapped. It's as if we found a tape measure woven into the fabric of space itself, letting us gauge expansion with extraordinary precision. Here's the brilliance of this method. Unlike supernova or Cepheid stars, baryon acoustic oscillations don't rely on brightness, which can be obscured by dust or measurement errors. They're a geometrical tool immune to the cosmic fog that blurs other techniques. By comparing the original size of these frozen ripples to their apparent size today, astronomers can calculate how much space has expanded, and the answer aligns eerily well with other probes like the cosmic microwave background. Yet it also deepens the Hubble tension, reinforcing the mystery of why different methods yield slightly different expansion rates. These oscillations do more than measure growth, they expose the universe's skeleton. The same waves that sculpted galaxy clusters also seeded the vast cosmic web of filaments and voids we see now. Every time astronomers map millions of galaxies and spot that telltale 500 million light-year preference, they're glimpsing the ghostly aftershocks of the Big Bang itself, a rhythm that still guides the universe's expansion like a metronome ticking across 14 billion years. Among the countless stars that flicker in the night, certain explosions shine with such consistent brilliance that astronomers use them as cosmic lighthouses markers to measure the vast distances of the universe. These are type Ia supernovae, the thermonuclear detonations of white dwarf stars, and they hold a unique power. Each one erupts with nearly identical peak brightness, like light bulbs manufactured to the same precise wattage. This uniformity makes them invaluable standard candles, objects whose true luminosity we know, allowing us to calculate their distance by how dim they appear from Earth. But in the late 1990s, these stellar explosions did more than just map the cosmos. They revealed its accelerating expansion, upending our understanding of cosmic fate. The magic of a type Ia supernova lies in its explosive trigger. Imagine a dense white dwarf, the smoldering core of a dead star, stealing gas from a neighboring star until it reaches a critical mass, 1.4 times the Sun's weight. At that precise threshold, the star can no longer support its own weight, and carbon fusion ignites like a runaway thermonuclear chain reaction. The entire star detonates in seconds, shining brighter than an entire galaxy. Because this detonation always happens at the same mass limit, the brightness is remarkably consistent, varying by less than 15%. It's as if nature handed astronomers a fleet of identical flashlights scattered across space, each one allowing us to gauge how far its light traveled before reaching us. When two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search, began collecting these cosmic beacons in the 1990s, they expected to confirm the universe's expansion was slowing under gravity's pull. Instead, they found the opposite, distant type Ia supernova, whose light had traveled billions of years to reach us, were significantly dimmer than predicted. Not because the explosions themselves were weaker, but because the space between those supernovae and Earth had stretched more than anyone anticipated. The universe wasn't just expanding, it was accelerating, as if some invisible force were shoving galaxies apart faster over time. The implications were staggering. For decades, cosmologists had assumed gravity would gradually reign in cosmic expansion, like a ball tossed upward, slowing as it climbs. These supernovae revealed the ball was instead rocketing skyward, defying gravity's grip. The discovery earned team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, and introduced the world to dark energy, the mysterious driver behind this runaway expansion. But Type Ia supernova aren't perfect yardsticks. Interstellar dust can dim their light, mimicking greater distances. Their brightness also depends slightly on how quickly they fade, requiring careful calibration. Yet even with these quirks, they remain one of our most powerful tools for measuring cosmic growth. By combining their data with other probes, like baryon acoustic oscillations or the cosmic microwave background, we've built a multi-pronged case for acceleration. Each supernova is like a checkpoint in a cosmic relay race, passing the baton of evidence across billions of years, reminding us the universe is stranger than we ever dreamed. Quasars are the universe's lighthouses, beacons so bright they outshine entire galaxies, visible from the edge of time itself. These aren't stars but the blazing cores of young galaxies, where supermassive black holes, billions of times the sun's mass, gorge on gas and dust. The energy released is mind-boggling. A single quasar can blaze with the light of 1 trillion suns, turning them into cosmic signposts we can spot from over 13 billion light-years away. But their brilliance isn't just spectacle, it's a tool. Quasars pierce through the fog of cosmic history, letting astronomers measure expansion in ways other objects can't. Here's how they crack the code. As light from a quasar streaks across the universe, it passes through vast clouds of intergalactic gas. These clouds absorb specific wavelengths of light, leaving dark lines in the quasar's spectrum like barcodes. But because space is expanding, those barcodes stretch, shifting toward the red end of the spectrum, the same redshift effect seen in galaxies. By comparing the absorption lines from multiple quasars at different distances, astronomers can track how expansion has changed over billions of years. It's like finding a stack of letters mailed from different eras, each stamped with the universe's growth rate at the time it was sent. Quasars also help map the cosmos in 3 dimensions. Projects like the Sloan Digital Sky Survey have used them to chart the universe's large-scale structure, revealing a cosmic web of galaxies and voids stretching across billions of light-years. Because quasars are so bright, they act as backlights, illuminating the faint gas filaments between galaxies that would otherwise remain invisible. Imagine shining a flashlight through fog. The beams reveal the hidden swirls and gaps in the mist. Quasars do the same for the universe, exposing the scaffolding of reality itself. The most astonishing part, some of the quasars we observe no longer exist. Their light has traveled so long that by now their black holes may have quieted, their galaxies matured into something unrecognizable. Yet their ancient glow still carries secrets, etching the universe's expansion history into photons that spent eons racing toward us. In their flicker, we glimpse an era when the cosmos was young, expansion was slower, and dark energy hadn't yet taken the wheel, a snapshot of the universe learning how to stretch. Gravity doesn't just pull, it bends. When light from a distant galaxy travels past a massive object like a galaxy cluster, space-time itself warps, twisting the light's path like a funhouse mirror. This effect, called gravitational lensing, isn't just a cosmic illusion, it's one of our most powerful tools for measuring the universe's expansion. Imagine holding a magnifying glass over a newspaper. The letters behind it stretch and distort. Now replace the magnifying glass with a galaxy cluster weighing a quadrillion suns, and the newspaper with light from the early universe. The result: stretched arcs, smeared galaxies, and perfect rings of light that Einstein himself predicted a century ago. The most striking examples are Einstein rings, halos of warped light where a distant galaxy's image gets bent into a full circle around a foreground cluster. Hubble's keen eye has captured dozens of these celestial bullseyes, each one a snapshot of spacetime's flexibility. But the real magic happens when astronomers use these distortions as cosmic scales. By measuring how severely the light bends, they can calculate the cluster's mass, and by comparing the lensed galaxy's redshift to its apparent position, they can triangulate how much space has stretched during the light's journey. It's like finding a ruler etched into the sky where the markings are written in warped starlight. These lensed galaxies also act as time machines. Some of the magnified arcs we see are from galaxies so far away their light has traveled over 12 billion years to reach us. Without the cosmic magnifying glass of a foreground cluster, their faint glow would be invisible. But gravity's twist amplifies their light, letting us study eras when the universe's expansion was still slowing under gravity's grip. The distortions aren't just pretty, they're precise. By mapping thousands of lensed galaxies, projects like the Dark Energy Survey have pinned down the expansion rate with rival accuracy to supernova or baryon acoustic oscillations. Yet lensing reveals something even deeper: the distribution of dark matter. Since dark matter doesn't emit light, its presence is only betrayed by how it warps the light of objects behind it. The sheer number of distorted galaxies in Hubble's deep field images suggests dark matter isn't just a shadowy halo around galaxies, it's a sprawling cosmic scaffold, bending spacetime on scales we're only beginning to map. Every arc, every ring, is a clue to the invisible architecture of the universe and how its hidden bulk steers the expansion we strain to measure. The beauty of gravitational lensing is its honesty. Light doesn't lie about the shape of space-time, it simply follows the curves gravity carves, and in those curves we find answers to questions Einstein himself might never have dreamed to ask. The cosmic microwave background isn't just a uniform glow, it's a whisper from the newborn universe, carrying secrets about expansion imprinted in its faint temperature variations. When the Planck satellite mapped this afterglow with unprecedented precision, it revealed a patchwork of microscopic hot and cold spots, fluctuations no larger than 1 part in 100,000. To the naked eye, the image looks like static on an old television, but to cosmologists, it's a Rosetta Stone. Those tiny ripples are frozen sound waves from a time when the universe was a seething plasma, just 380,000 years old. Zoom in, and each fluctuation tells a story. The hotter regions mark where matter was slightly denser, pulled together by gravity's grip, while cooler patches trace the valleys where matter was more thinly spread. These imperfections weren't random, their size and distribution were shaped by the universe's expansion rate during those first critical moments. Like fingerprints left in wet cement, they preserve the push and pull between gravity's inward tug and dark energy's outward push, a battle that set the stage for everything that followed. The Planck data's real power lies in its predictability. The physics of the early universe dictates that these fluctuations should follow a specific pattern, like the harmonics of a musical instrument. By measuring the angular size of the most common hotspots, roughly 1 degree across, scientists could calculate how much the universe has expanded since the light was emitted. The result, a Hubble constant of 67 kilometers per second per megaparsec, a value that aligns perfectly with other probes like baryon acoustic oscillations but deepens the mystery of why local measurements disagree. These temperature variations also encode the universe's composition. The way they're spaced reveals how much ordinary matter, dark matter, and dark energy filled the cosmos, like deducing a cake's recipe by studying its crumb structure. Dark matter's gravity sculpted the larger ripples, while dark energy's influence shaped how those patterns stretched over time. The Planck map is more than a baby picture. It's a diagnostic tool, revealing the universe's vital signs at the moment it first blinked into transparency. Yet the most astonishing detail is how small these fluctuations are. That near-perfect uniformity, those minuscule deviations, were all gravity had to work with to build galaxies, stars, and eventually us. Without those tiny seeds, those quantum whispers amplified by inflation, the cosmos might have remained a featureless void. The cosmic microwave background isn't just a relic. It's the blueprint for everything, and its faint wrinkles are the reason we're here to study them at all. Quantum physics tells us that empty space isn't really empty, it crackles with energy, a seething quantum foam where particles flicker in and out of existence in an endless dance. This vacuum energy should, in theory, drive the expansion of the universe, acting as Einstein's cosmological constant, a repulsive force embedded in spacetime itself. But here's where the math goes off the rails. When physicists calculate how much energy this quantum frenzy should produce, they land on a number so catastrophically large it defies comprehension. 10 to the power of 120 times stronger than what we actually observe. That's a 1 followed by 120 zeros, a discrepancy so vast it's been called the worst theoretical prediction in the history of physics. Let's put that absurdity into perspective. If the vacuum energy were even a fraction of what quantum theory suggests, the universe would have torn itself apart nanoseconds after the Big Bang. Stars wouldn't just fail to form, atoms couldn't hold together. Yet here we are in a cosmos where vacuum energy is whisper weak, exerting just enough repulsion to accelerate galaxies apart without instantly unraveling reality. This mismatch isn't just a rounding error. It's like predicting a hurricane and getting a gentle breeze instead, except the hurricane should have enough force to obliterate the observable universe 10 to the power of 120 times over. The mystery cuts to the heart of modern physics. Either we're missing something fundamental about quantum field theory, or there's a cosmic cancellation mechanism we haven't discovered, some symmetry or principle that nearly perfectly neutralizes vacuum energy's brute force, leaving behind only the faintest residue we call dark energy. String theorists have proposed exotic solutions involving extra dimensions, while others speculate that an unknown law of nature suppresses vacuum fluctuations at large scales. But so far, no explanation fully bridges the gap between prediction and observation. This isn't just academic hand-wringing. Dark energy's feeble strength is the sole reason galaxies, planets, and life exist. If it matched quantum theory's prediction, space would expand so violently that gravity could never pull matter together. The universe would be a thin, lifeless mist. Instead, we inhabit a Goldilocks cosmos where vacuum energy is bizarrely, inexplicably tiny, a whisper in a calculation that screams. The vacuum catastrophe isn't just an unsolved problem. It's a blazing signpost pointing to gaps in our understanding so profound they might rewrite the laws of physics. Picture this: dark energy isn't just a constant force, it grows stronger, denser, more ravenous with time, like a fire fed by the fabric of space itself. This nightmare scenario has a name: phantom energy, a hypothetical form of dark energy that doesn't just accelerate cosmic expansion but escalates without limit. If real, it wouldn't merely push galaxies apart. It would tear space-time apart at the seams, culminating in the most violent endgame imaginable, the Big Rip. Here's how the math unfolds. Right now, dark energy's repulsive force is weak, barely noticeable across local galaxies. But if it were phantom energy, its strength would scale with the volume of space it inhabits, meaning the more space expands, the more phantom energy emerges, creating a runaway feedback loop. The universe's stretching wouldn't just continue, it would explode, doubling in speed over shorter and shorter intervals. First, galaxy clusters would be ripped apart, their gravitational bonds overwhelmed. Then individual galaxies would disintegrate, stars spiraling into the void. Planets would be peeled from their orbits, and finally, in the last horrific microseconds, even atoms would be shredded as the repulsive force overpowers the very glue holding nuclei together. Estimating the timeline requires some cosmic arithmetic. Current observations suggest the Big Rip, if it happens at all, wouldn't occur for another 22 billion years, long after the Sun has died and the Milky Way has merged with Andromeda. But if phantom energy's equation includes a particularly steep growth rate, that deadline could shrink dramatically. Some models hint at a mere 60 billion years before the universe's fabric is torn asunder, though the uncertainties are vast. There's an eerie irony to this scenario. The same force that once helped galaxies form, dark energy's gentle push against gravity, could, under different rules, become the universe's executioner. Yet the Big Rip isn't just a doomsday tale, it's a stress test for our understanding of physics. If dark energy can evolve, then the cosmos might be far more dynamic and far more fragile than we ever dared imagine. What if our universe isn't the only one? Imagine a cosmic foam bubbling endlessly with pocket universes, each expanding at its own rate, some too fast for stars to form, others collapsing instantly. This isn't sci-fi, it's a serious theory called eternal inflation, where the fabric of reality isn't just stretching, it's birthing new universes like bubbles in a boiling pot. And here's the kicker. In this infinite multiverse, our universe's Goldilocks expansion rate, not too fast, not too slow, might be a rare fluke, a cosmic lottery win that made life possible. Think of it like blowing soap bubbles. Each one inflates on its own, with some popping immediately while others drift away. In eternal inflation, space expands exponentially, but tiny quantum fluctuations can trigger bubble nucleation, regions where inflation suddenly stops, creating isolated universes with their own physics. Some might expand so violently that matter never clumps into galaxies. Others could collapse back into singularities before time even begins. Ours just right, with a Hubble constant that allowed galaxies, planets, and eventually us to exist. This idea isn't just wild speculation. The math behind inflation naturally leads to multiverse predictions, and our universe's finely tuned expansion rate fits uncomfortably well with the idea of infinite variance. If dark energy was slightly stronger, galaxies would have been ripped apart before life could emerge. Slightly weaker, and gravity would have crunched everything back into a black hole. The odds of hitting this balance by chance seem absurdly low, unless there are countless universes where the numbers rolled differently, and we just happen to be in the one where the dice landed perfectly. Critics argue this is untestable philosophy, not science. But some theories suggest bubble universes might leave imprints in our cosmic microwave background, circular bruises from collisions with neighboring universes. Others propose that advanced civilizations in distant bubbles could send gravitational wave signals, though detecting them remains a pipe dream. For now, the multiverse remains a tantalizing what if, a framework that turns our universe's life-friendly expansion from a miracle into a statistical inevitability across infinite realities. The haunting implication: if most universes are sterile, our existence isn't just lucky. It's a fleeting anomaly in a vast cosmic graveyard where trillions of dead universes expanded too fast or too slow to ever spark life. And that makes every star in our sky feel infinitely more precious. Down at the smallest scales, imaginable trillions of times tinier than an atom, spacetime isn't the smooth fabric we picture. It's a writhing, frothing storm of quantum foam, where virtual particles flicker in and out of existence so fast they defy the very notion of empty space. This isn't just microscopic chaos, it's a fundamental feature of reality that might hold clues to why the universe expands the way it does. Picture the cosmos as an ocean. From a distance, the surface looks glassy and serene, but zoom in close enough and you'll see turbulent waves, whirlpools, and bubbles constantly forming and popping. That's quantum foam, spacetime itself boiling with energy at the Planck scale, roughly 10 to the power of -35 meters. Now here's where it gets wild. Some theories suggest this frothiness doesn't just stay small, it could leave fingerprints on the universe's expansion. One radical idea from loop quantum gravity, an alternative to string theory, proposes that spacetime is woven from tiny, indivisible loops. These loops don't just sit there, they interact dynamically, creating a granular structure that might subtly alter how space stretches over cosmic distances. Think of it like stretching a piece of fabric woven from elastic threads. If the threads have unique properties, say, they resist stretching past a certain point, the whole cloth might expand differently than if it were perfectly smooth. Loop quantum gravity hints that spacetime's granularity could tweak the equations governing cosmic acceleration, potentially offering a bridge between quantum mechanics and general relativity. The implications are staggering. If quantum foam affects expansion, it might help explain why dark energy is so unfathomably weaker than quantum theory predicts. Perhaps the frothiness cancels out most of vacuum energy's repulsive force, leaving behind just the faint whisper we call dark energy. Or maybe the foam's turbulence generates tiny fluctuations that accumulate over billions of light years, nudging galaxies apart faster than expected. Either way, the universe's largest-scale behavior might be rooted in its smallest-scale structure, a cosmic conspiracy linking the infinitesimal to the infinite. Yet testing these ideas is brutally hard. Quantum foam's effects are so minuscule that current technology can't probe it directly. Some experiments hunt for indirect clues, like subtle variations in the speed of light that might betray spacetime's granularity. Others look for imprints in the cosmic microwave background, searching for patterns that only a foamy spacetime could create. Until we crack the quantum gravity code, these remain tantalizing what-ifs. But they remind us that the universe's expansion isn't just a story of galaxies flying apart. It's a saga written in the hidden language of spacetime itself, from its tiniest tremors to its grandest sweeps. What if the speed of light wasn't always constant? For over a century, Einstein's cosmic speed limit, 299,792 kilometers per second, has been treated as an unchanging law of nature. But a handful of physicists propose a radical alternative. In the fiery chaos of the early universe, light might have raced across space much faster than it does today. This isn't just an academic tweak if true. It could rewrite how we measure cosmic expansion, offering a way out of the Hubble tension and other cosmological headaches. The idea, known as variable speed of light theories, flips conventional wisdom on its head. Mainstream cosmology assumes light speed has remained fixed since the Big Bang, acting as a reliable yardstick for distances across the cosmos. But proponents like physicist JWST suggest that in the first sliver of a second after creation, light could have traveled exponentially faster, then slowed abruptly as the universe cooled. Picture a highway where the speed limit starts at 1,000,000 kilometers per hour, then drops to 100 as traffic builds, except here, the traffic is the thickening fabric of spacetime itself. Why consider such a heresy? For starters, it could explain some stubborn puzzles. If light moved faster in the early universe, it would have reached distant regions before they drifted beyond contact, solving the horizon problem without needing cosmic inflation's explosive growth spurt. It might also account for the universe's eerie large-scale uniformity. No need for inflationary smoothing if light had enough speed to mix everything while the cosmos was still compact. Even the Hubble tension could soften if changing light speeds threw off our distance measurements across different epochs. Critics, however, aren't swayed. The standard model of cosmology relies on light's constancy to synchronize everything from galaxy redshifts to the cosmic microwave background. Tampering with that foundation threatens to unravel decades of precise predictions. Worse, no direct evidence supports light speed ever changing, just mathematical models showing it could have happened without breaking known physics. The cosmic microwave background's near-perfect blackbody spectrum, for instance, aligns perfectly with constant light speed predictions, leaving little room for alternatives. Yet the debate isn't purely academic. If variable light speed theories gain traction, they'd force a seismic shift in how we interpret cosmological data. Supernova distances, baryon acoustic oscillations, even the apparent acceleration of dark energy all rely on light speed as a fixed reference. If that reference was slippery in the past, our expansion rate measurements might need recalibration, potentially reducing or eliminating the need for dark energy's mysterious push. The irony is delicious. Einstein's theory of relativity, which enshrined light speed as the universe's ultimate constant, might one day bend to accommodate its own revolution. For now, these ideas linger at the fringe, provocative thought experiments challenging orthodoxy from the shadows. But in cosmology, today's heresy often becomes tomorrow's textbook. After all, the universe has a habit of surprising those who claim to know its rules too well. What if our cosmic neighborhood is emptier than we thought? Astronomers have stumbled upon a puzzling possibility that we might be sitting inside a vast bubble of nothingness, a region where galaxies are strangely sparse compared to the rest of the universe. This hypothetical void, named the KBC void after astronomers Keenan, Barger, and Cowie who proposed it, spans a staggering 2 billion light-years across, making it the largest known structure of its kind. If real, this underdense region could be warping our measurements of cosmic expansion, tricking us into thinking the universe is expanding faster nearby than it truly is. Here's how the illusion works. Imagine standing in a valley surrounded by mountains. If you didn't know about the mountains, you might assume the ground sloped downward everywhere, just as we might misjudge the universe's expansion if we're inside a cosmic valley of missing matter. In this scenario, the gravitational pull from surrounding denser regions would subtly tug galaxies outward, making nearby space appear to stretch faster than the cosmos at large. The local Hubble constant would seem higher not because expansion itself has changed, but because our perspective is skewed by the void's emptiness. The KBC void isn't just idle speculation. Observations reveal our local galactic neighborhood is about 20% emptier than average, with galaxy counts dropping noticeably within 500 million light-years. Supporters argue this underdensity could explain at least part of the Hubble tension, the nagging discrepancy between local and early universe expansion measurements. If we account for the void's gravitational effects, the gap between 67 and 73 kilometers per second per megaparsec might narrow, easing cosmology's biggest headache. But not everyone's convinced. Critics point out that a void this large defies standard cosmic models, which predict matter should be more evenly distributed. Creating such a colossal emptiness would require near-impossible fine-tuning in the early universe's density fluctuations. Even if it exists, simulations suggest the KBC void's impact on the Hubble constant would be modest, shaving off maybe 1 or 2 units from the tension, not solving it outright. Worse, some galaxy surveys find no evidence for such a drastic underdensity, painting our local universe as fairly ordinary. The debate rages because the stakes are high. If the void is real, it reshapes our understanding of cosmic structure and forces us to recalibrate decades of expansion measurements. If not, the Hubble tension becomes even more baffling, hinting at deeper cracks in our cosmological framework. Either way, the KBC void forces us to ask an unsettling question. Are we cosmic outliers peering out from an unrepresentative pocket of space? And if so, what else might we be getting wrong about the universe's grand expansion? Neutrinos are the universe's ghost particles so elusive they pass through entire planets without a single collision. Born in the nuclear furnaces of stars and supernovae, these nearly massless wanderers outnumber atoms 1 billion to 1, flooding the cosmos in an invisible tide. Yet for all their subtlety, they've left a faint gravitational fingerprint on cosmic expansion, tugging ever so gently on the fabric of space-time during the universe's formative years. Picture the cosmos in its first few minutes, a seething plasma so hot and dense that even neutrinos, which rarely interact with matter, were trapped in the chaos. As the universe expanded and cooled, these particles broke free, streaming outward at nearly the speed of light. But unlike photons, which were held back by constant collisions until the cosmic microwave background was born, neutrinos slipped away almost immediately, forming a vast, diffuse sea that permeated everything. Their escape mattered because even ghostly particles exert gravity. While each neutrino's pull was vanishingly weak, their sheer numbers added up, creating a collective gravitational effect that subtly resisted the universe's expansion. Here's the twist: neutrinos didn't just slow things down, they left behind a unique signature in how structures formed. As they raced outward, their gravity tugged on matter, smoothing out some of the primordial lumpiness that would later seed galaxies. This delicate interference is imprinted in the cosmic microwave background's faint temperature variations, where precise measurements reveal slightly fainter fluctuations than expected, a whisper of neutrinos' restraining influence. Modern telescopes like Planck have detected this signature, confirming that neutrinos, despite their minuscule mass, played a measurable role in shaping the cosmos. Yet their impact was fleeting. As the universe swelled, neutrinos lost energy, slowing from relativistic speeds to a cosmic crawl. Today, they drift as a cold background bath, their gravitational influence dwarfed by dark energy's relentless push. But in those early moments when the universe's fate hung in the balance, these spectral particles were silent architects, bending spacetime just enough to leave their mark on everything that followed. Their story is a reminder that even the faintest forces can shape the grandest designs. Picture a night sky 500 billion years from now, not twinkling with distant galaxies but eerily dark. The accelerating expansion of space is already erasing entire galaxies from our cosmic view, like lights dimming on a receding shore. Right now, we can observe trillions of galaxies through powerful telescopes. But in the distant future, every galaxy beyond our local group, a small cluster of about 80 galaxies bound together by gravity, will vanish from sight, their light stretched beyond detectability as space itself carries them away faster than their photons can reach us. At first, the changes will be subtle. Galaxies at the universe's current edge will redden, their light stretched into infrared invisibility as expansion accelerates. Over eons, even closer galaxies will seem to freeze in time, their light growing dimmer and more redshifted until they fade like dying embers. The Andromeda Galaxy, destined to collide with the Milky Way in about 4 billion years, will remain visible, but everything beyond our gravitationally bound neighborhood will slip behind an invisible curtain. Future astronomers will peer into the void and see nothing but blackness, with no evidence that countless galaxies ever existed. This isolation isn't just about visibility, it's about lost history. The light arriving from distant galaxies today carries clues about the universe's youth. When those galaxies vanish, so does our window into cosmic origins. Imagine a library burning book by book, leaving only the spines of a few volumes on the shelf. Future civilizations, no matter how advanced, will have no way to study the cosmic microwave background, measure the Hubble Constant, or grasp the universe's accelerating expansion unless they've decoded the secrets of their local stars and deduced the truth from fragments. The cruelest irony: some of these doomed galaxies might still exist when their light stops reaching us. Their stars could burn for trillions of years, their planets hosting life, but their signals will never arrive. Like two ships drifting apart in a rising tide, space's expansion severs the connection forever. Future civilizations may never know they're not alone, trapped in a cosmic oasis, surrounded by an unreachable desert of darkness. Yet even this bleak future holds a strange beauty. The stars of the local group will eventually merge into a single supergalaxy, its glow warming whatever life remains. Against the infinite black, their light will be the only proof that the universe ever held anything at all. The accelerating expansion may erase the cosmos from view, but in the darkness, those who remain will inherit the last island of light. Black holes will be the last survivors of the cosmic apocalypse. In a future so distant it makes stars seem fleeting, some 10 to the power of 100 years from now, the accelerating expansion of space will have carried away every galaxy, every star, even the faintest wisp of interstellar gas. Only black holes will remain, drifting in perfect darkness like tombstones in an endless graveyard. These gravitational monsters, formed from collapsed stars and galactic cores, are the universe's ultimate bunkers, so dense that not even light can escape their grip. Yet even their reign won't last forever. Thanks to a bizarre quantum quirk called Hawking radiation, black holes slowly leak energy, evaporating particle by particle until they vanish in a final puff of radiation. Here's how the end game unfolds. As space stretches toward infinity, matter becomes impossibly sparse. Black holes, cut off from new material to consume, enter starvation mode. Their only sustenance comes from the faint glow of virtual particles popping in and out of existence at their event horizons, a process predicted by Stephen Hawking in 1974. Quantum mechanics allows pairs of particles to briefly form near a black hole's edge. Sometimes one falls in while the other escapes, stealing a tiny bit of the hole's mass in the process. Over incomprehensible timescales, this drip feed of lost energy causes black holes to shrink, their temperatures soaring as they diminish. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate. A supermassive one far longer, but in this era time has lost all meaning. With no stars left to mark its passage, the universe becomes a silent theater where the only events are the occasional pops of dying black holes. The largest, those weighing billions of suns, will outlast their smaller kin by orders of magnitude, clinging to existence as space grows colder and emptier. Their final moments will be the last bursts of light in a cosmos that's otherwise faded to absolute zero, brief flashes signaling the end of structure itself. The eerie beauty of this epoch is its inevitability. No force can stop it. Dark energy's relentless push ensures that everything not bound by gravity will be lost to the void, and gravity's strongest knots, black holes, are undone by quantum mechanics, the very rules that once helped shape the universe. It's a poetic demise, the mightiest objects in creation, brought low by the tiniest flickers of uncertainty at the edge of reality. Yet even in this bleak future, there's a strange glimmer of rebirth. Some theories suggest the radiation from evaporating black holes could seed new universes in a multiverse beyond our own, scattering quantum fluctuations that might one day spark another Big Bang. If true, black holes wouldn't just be the last chapter of our story, they'd be the prologue to another. What if the universe's expansion rate isn't just a number, it's a cosmic prerequisite for life itself? The anthropic principle whispers a tantalizing possibility that the conditions we observe, from the force of gravity to the speed of light, aren't arbitrary. They're the only ones that could have allowed galaxies, stars, and ultimately us to exist, and the expansion rate, it's no exception. Tweak it even slightly, and the entire cosmic drama collapses before the first act. Imagine a universe where expansion raced just a fraction faster after the Big Bang. Matter would have spread too thin, pulled apart before gravity could sculpt it into stars. No stars mean no heavy elements, no carbon, no oxygen, no building blocks for planets or life. Now picture the opposite, expansion creeping too slow. Gravity would have won too soon, dragging everything back into a crushing Big Bang in reverse before galaxies could ignite. The balance is so precise it defies coincidence. For atoms to assemble into astronomers, the universe had to grow at exactly the right speed. Not too fast, not too slow, but just enough to let gravity carve islands of matter in a sea of expanding space. This fine-tuning isn't just theoretical. Calculations show that if the initial expansion rate had varied by even 1 part in 100,000 billion, the cosmos would have been sterile. Stars need time to form, and life needs stars to forge the elements that make it possible. The expansion rate isn't just a dial on the universe's size, it's a timer setting the pace for every structure that emerges. Too fast and the timer runs out before gravity can clump matter. Too slow and the clock resets in a cosmic crunch. Yet the anthropic principle doesn't answer why this perfect balance exists, only that we're here to observe it. Some argue it's evidence of deeper physics yet to be discovered, a law that locks expansion to life-friendly values. Others see a multiverse where countless universes bubble into existence, each with random expansion rates, and we simply inhabit the rare one where the numbers lined up. Either way, the universe's expansion isn't just a backdrop, it's a silent architect shaping reality with a precision that borders on the miraculous. For decades, dark energy has been the leading explanation for the universe's accelerating expansion. But what if we're missing something simpler? A small group of physicists propose a radical alternative. Perhaps gravity itself behaves differently on cosmic scales than Einstein predicted. Enter modified Newtonian dynamics, or MUND, a theory that rewrites the rules of gravity to explain galactic motions without invoking invisible dark matter or dark energy. Instead of mysterious substances shaping the cosmos, MUND suggests our understanding of gravity is incomplete, especially in the weak field regime where accelerations become vanishingly small. The roots of MUND trace back to astrophysicist Mordechai Milgrom's work in the early 1980s. He noticed something peculiar about spiral galaxies. Their outer stars rotated far faster than Newtonian physics predicted, as if some unseen mass were anchoring them in place. But rather than inventing dark matter, Milgrom proposed a simple tweak that Newton's laws break down at extremely low accelerations, below about 1/10 billionth of a meter per second squared. At these scales, gravity might strengthen slightly, mimicking the effects of extra mass. Remarkably, this single adjustment reproduced galaxy rotation curves with surprising accuracy, no dark matter required. MUND's appeal lies in its elegance. Where standard cosmology requires 95% of the universe's content to be invisible and unexplained, MUND offers a minimalist fix, changing one equation to account for observations. It's like realizing you've been misreading a map for centuries. The terrain hasn't changed, but your compass has. Supporters point to MUND's uncanny success in predicting galaxy dynamics, even in cases where dark matter models struggle. For example, some ultra-diffuse galaxies show motions that align perfectly with MUND predictions but baffle conventional theories. Yet the theory faces formidable hurdles. While MUND excels at galaxy-scale phenomena, it stumbles when applied to larger structures like galaxy clusters, where additional mass, possibly dark matter, still seems needed to explain gravitational lensing and hot gas distributions. Worse, MUND struggles to account for the cosmic microwave background's precise fluctuations or the universe's accelerating expansion without reintroducing something akin to dark energy. Critics argue it's a local solution to a global problem, like patching one leak in a sinking ship while ignoring the others. The debate intensifies when considering relativistic extensions of MUND, such as TVS tensor vector scalar gravity, which attempt to reconcile Milgrom's ideas with Einstein's framework. These theories introduce additional fields that modify gravity's behavior, but they often feel ad hoc, stitching together fixes without the simplicity that made original MUND appealing. Meanwhile, direct detections of gravitational waves have so far aligned perfectly with Einstein's predictions, leaving little room for alternative gravity models to maneuver. The stakes are high. If MUND or a successor theory could fully replace dark energy, it would revolutionize cosmology, demoting one of science's greatest mysteries to a mere miscalibration of gravity. But until it can explain the full spectrum of cosmic evidence, from galaxy rotations to the Hubble tension, it remains a provocative underdog in the quest to understand expansion. For now, dark energy still holds the lead, but the race is far from over. The universe's acceleration might yet surprise us with answers no one has dreamed of. James Webb's infrared gaze is peeling back layers of cosmic history, revealing the universe's infancy with unprecedented clarity. Unlike Hubble, which sees primarily invisible light, JWST detects the faintest infrared whispers from galaxies so ancient their light has been stretched into near invisibility by expansion. These aren't just pretty pictures, they're time capsules, capturing moments when the cosmos was a mere 2% of its current age. Already, Webb's data has upended expectations, spotting fully formed galaxies where theory predicted only primordial chaos. Their unexpected maturity suggests structure coalesced faster than models predicted, hinting that dark energy's influence, or something else entirely, might have played tricks on the early universe's expansion rate. One of Webb's most tantalizing targets, the very first generation of stars known as population Roman 3, these hypothetical giants, hundreds of times the Sun's mass, forged the universe's first heavy elements in their cores. Spotting their faint glow would anchor our understanding of cosmic dawn, providing a critical benchmark for expansion measurements. But Webb's infrared vision isn't just about glimpsing the past, it's about recalibrating the cosmic ruler. By observing Cepheid variable stars and ancient supernovae in galaxies Hubble struggled to resolve, JWST is refining distance measurements with razor precision. Early results suggest some Cepheids are slightly farther away than previously thought, potentially nudging the local Hubble constant downward, a small but crucial step toward reconciling the tension with early universe data. Yet Webb's most revolutionary contribution might be its ability to probe the Dark Ages, the murky epoch before stars flickered to life. By mapping the distribution of primordial hydrogen with its spectroscopic tools, JWST could reveal subtle variations in the universe's early expansion, offering clues about dark energy's primal strength. Some theorists speculate that if dark energy's density has changed over time, Webb's observations of ancient galaxy clusters might catch it in the act, exposing a dynamic force rather than Einstein's static cosmological constant. The stakes are cosmic. If JWST confirms that galaxies formed too early or clustered too densely, it could imply an expansion history radically different from textbook models, perhaps even pointing toward exotic physics like interacting dark matter or extra dimensions. Every data stream from Webb's golden mirrors is a potential key to unlocking the Hubble tension, not by favoring one side over the other, but by revealing a deeper story where both early and modern measurements are pieces of a puzzle we've only begun to assemble. The universe's expansion rate isn't just a number, it's a narrative written in starlight, and JWST is translating its earliest chapters for the first time. You don't need a PhD to help unravel the mysteries of cosmic expansion, just a curiosity for the cosmos and an internet connection. Projects like Galaxy Zoo have turned galaxy classification into a global collaboration where everyday stargazers can contribute to real scientific discovery. Imagine scrolling through stunning images of distant galaxies captured by telescopes like Hubble, clicking to categorize their shapes: spiral, elliptical, or irregular. Each classification helps astronomers map how galaxies evolve and cluster, piecing together the universe's expansion history like a cosmic jigsaw puzzle. What makes this revolutionary isn't just the scale. Over 150,000 volunteers have joined since Galaxy Zoo launched in 2007, but the way it taps into human intuition. Even the most advanced algorithms struggle to match our brain's knack for spotting patterns, especially in messy, distant galaxies where quirks like mergers or dust lanes confuse computers. Volunteers have identified rare green pea galaxies, spotted gravitational lenses missed by professionals, and even uncovered entirely new galaxy types like Hannes Voorwerp, a mysterious gas cloud discovered by a Dutch schoolteacher. These finds aren't just curiosities, they refine how we measure galactic distances and motions, key ingredients in calculating expansion rates. The beauty of citizen science lies in its accessibility. While cutting-edge telescopes like JWST gather terabytes of data, there's more information than astronomers can process alone. Platforms like Zooniverse Galaxy, Zoo's parent project, offer dozens of space-related tasks, from hunting supernova to tracing gas clouds in radio telescope images. Some projects focus explicitly on expansion, like Dark Energy Explorers, where volunteers help identify galaxy clusters to probe dark energy's influence on large-scale structure. Others, like Backyard Worlds, invite participants to scour infrared surveys for rogue planets or brown dwarfs, indirectly refining our cosmic distance ladder. This crowdsourced approach isn't just efficient, it's transformative. In 2013, Galaxy Zoo volunteers helped confirm that red spirals, a rare galaxy type, are more common in dense regions of the universe, a clue about how environment affects galactic aging. Such insights feed into models of cosmic evolution, helping astronomers test whether expansion rates vary across different galactic neighborhoods. And the data isn't just for pros. Many projects release their findings publicly, empowering amateurs to conduct their own research or even co-author papers. Over 50 scientific publications have credited Galaxy Zoo participants as collaborators, proving that discovery isn't confined to ivory towers. The next breakthrough could come from your laptop. Whether you spend 5 minutes or 5 hours classifying galaxies, each click adds to a living map of the expanding universe. In an era where professional astronomy grows increasingly specialized, these projects remind us that the cosmos belongs to everyone, and that the keys to unraveling its grandest mysteries might lie in the collective curiosity of millions of eyes scanning the stars. After all these mind-bending discoveries about cosmic expansion, here's the humbling truth: we've only been studying the tip of the iceberg. The forces sculpting the universe's growth aren't just mysterious, they're practically invisible. Dark energy and dark matter, the twin shadows driving expansion, make up 95% of the universe's total content, yet we still don't know what they actually are. Think of it like watching a marionette show where the puppets dance with eerie precision, while the strings and hands controlling them remain utterly unseen. That's cosmology today. We measure the movements perfectly, but the puppeteers remain hidden in the dark. Dark matter, making up 27% of the cosmos, reveals itself only through gravity. Its invisible grip holds galaxies together, preventing them from flying apart as they spin. Without it, our Milky Way would shred itself like cotton candy in a hurricane. Yet despite decades of hunting, we've never directly detected a single dark matter particle. Underground labs, space telescopes, and particle colliders have all come up empty, leaving theories from WIMP to actions dangling in uncertainty. Then there's dark energy, the even more baffling 70%. Unlike dark matter's glue-like pull, dark energy pushes, a repulsive force embedded in space itself, stretching the cosmos faster with every passing second. Einstein's cosmological constant offers one explanation, but here's the kicker: quantum physics predicts vacuum energy should be unimaginably stronger than what we observe. Our best equations overshoot dark energy's measured strength by a factor of 1, followed by 120 zeros, the worst mismatch in scientific history. It's as if we calculated the weight of all oceans, then found only a single cup of water where they should be. This glaring gap isn't just embarrassing, it's an invitation. The universe's expansion rate isn't a solved equation. It's a flare lighting up the boundaries of our ignorance. Every anomaly, from the Hubble tension to phantom energy theories, hints that we might be missing entire chapters of physics. Maybe dark energy evolves over time, or perhaps gravity behaves differently across cosmic scales. Some even speculate that our universe is a bubble in a multiverse foam, with expansion rates varying wildly beyond our view. Yet uncertainty is where science shines brightest. Upcoming telescopes like the Vera Rubin Observatory and the Euclid Space Mission are mapping billions of galaxies to trace dark energy's fingerprints. Particle detectors buried deep underground still hunt for dark matter's whisper-thin interactions, and quantum gravity theories from strings to loops keep probing the space between our equations and reality. The cosmos isn't just expanding, it's daring us to keep up, dangling 95% of itself just out of reach. But that's the thrill of the hunt. Every unanswered question is a new starting line, and the finish line might rewrite reality itself. From the mind-bending redshift of fleeing galaxies to the invisible grip of dark energy, we've raced through 30 astonishing truths about the universe's expansion. The cosmos stretches faster than light can chase it. Ancient quasars whisper secrets across billions of years, and black holes will outlast even time itself. We've seen how supernova revealed acceleration, how cosmic inflation set the stage for everything, and how the Hubble tension keeps scientists awake at night. The universe isn't just growing, it's rewriting its own rules as it goes, leaving us scrambling to decode the changes. Here's the staggering truth: every second, the space between galaxies swells by a football field's length. Yet in this vast, accelerating dance of space-time, we've carved out a sliver of understanding, a flicker of insight against the darkness. The mysteries far outnumber the answers, but that's the thrill of the chase. Each fact we've uncovered is a stepping stone across an infinite river of questions. So what's your favorite cosmic revelation? The way quantum foam might shape expansion? The haunting future where galaxies vanish from view? Drop it in the comments. We're all stargazers here, piecing together the universe's grand puzzle one fact at a time. If this journey through space's stretching fabric left you awestruck, hit like, subscribe, and keep looking up. The cosmos isn't done surprising us yet.